In this brief section, I'm going to highlight a parameter that can help prevent the degradation of images, and that is an important thing to do. With the popularity of narrowband imaging today, this parameter has increased importance. It is possible, here's the problem, to inadvertently over-subtract a dark frame from data. And of no fault of the image processor, this is just occurring because these sensors, especially CMOS sensors, have such a low level of noise that it's possible to over-subtract and lose information. I'm going to show you what that loss of information looks like. It's subtle. You might not even know it's happening. You should check your data and prevent the issue by using this output pedestal to prevent this problem from ever occurring. Before I continue, let me just say, please like this video and subscribe to my channel. I'm not making money on this YouTube channel or any of these videos. I consider these videos a way to contribute to the astrophotography community and a way to get the word out, literally, so that you can really take advantage of the latest and greatest advances that might be occurring. Of course, if you do like this kind of content, I encourage you to become a member of Atom Block Studios, where you can learn more fully about the art and science of astrophotography, especially image processing. Okay, so now I'm going to demonstrate what the problem is, and that will really, I think, highlight what's going on here. I am going to open up an image that was kindly provided, this data, kindly provided by a gentleman named Adrian. And as I say, this effect, this loss of information is kind of subtle. So kudos to him for having this keen eye and noticing that there was an issue. So let's open up one of his raw HA frames here. It's a hydrogen alpha of Thor's helmet, and it looks like a perfectly reasonable HA image of this particular target. I'm also going to open up one of his dark frames because I would like to show you, without any other manipulation going on, what happens when I literally subtract this dark frame from his data. So let's go ahead and do that to make life easy. I'm going to call this a dark. I'm going to use Pixel Math to do this, so that's why I'm renaming these things, because I just want to show you straight up what it looks like. So we go to Pixel Math here, where we will say HA minus dark, which is what I called those images. We'll create a new image, and let's just generate that image and see what it looks like. So here it is. This is dark subtracted. In fact, I want to, just make it really clear that if we do this and then we match these two, so here's the original data here. I guess I have to resize it like that. And if we blink these two images, you'll see that the dark subtraction is exactly how you might expect it to be. You can see, for example, that all the hot pixels, these kinds of hot pixels here, they all go away. So we know the subtraction is working properly. And just zooming out, I don't know, that it's not plainly obvious to me that there is a degradation of this image. There's a loss of information, but Adrian noticed. He noticed that if he rolled his cursor, and I'll try to demonstrate this here somewhere, if you roll your cursor around and you find particular pixels here, let's zoom in some more so it'll be easier to see. Some of these pixels, oh, there was one. Some of these pixels record not a value, but an absolute zero value. Now, one little zero here, that might not be a big deal, right? But it is a loss of information. And the funny thing is, if you scroll around, you will eventually find that there are more zeros in this image. It is a loss of information. Now, you might still think that that's a subtle thing, but it's not. The problem is much worse than you might imagine. And let me just demonstrate that. The question is, how many zeros are in this picture? I'm going to show you one way to literally see all of the zero values here. We can, of course, this is the PixInsight way of doing things. We can make an expression here that will allow us to do this. So I'm going to make an expression that says if the value in the image, target T, whatever image we're looking at, if it equals 0, then light it up as something, as 1, which means make it a bright pixel. Otherwise, don't do anything at all. But if I did this expression on this image, it'll show me where the zeros are, but it'll make white pixels. And that's not very obvious as to what's going on because I already have white pixels here. So what I'm going to do is a trick. here's the trick. I'm going to make this image here. I'm going to make it a color image. It was a grayscale image, and now I'm making a color image so that this now refers to the red channel if I don't use a single expression. And then for the green and the blue channels, we want them to remain the same. And what that means is that this expression only applies to the red channel. So if it comes across a 0 in this image, it's going to light up the pixel as red. Are you ready? Let's do a replace image here. Set. There are the zeros. I hope you're impressed. This is a true degradation of the image, and you might not have known that this was going on. I encourage you, if you are doing narrowband imaging with relatively short exposures or one of these CMOS type cameras, just check once. Do this kind of thing. Look for those zeros. Make sure that you're not losing information. Every one of these little red blips here is an absolute 0 in this image, and that loss of information is going to hurt, because after you average all these images together, you will not be getting the full signal that you might hope to. Consider that what these zeros actually mean. What's going on is that when you subtract the dark frame, one of these zeros here could be -10, and then you might have in another 0 point that pixel might subtract out from the dark, and it might be -1000. And there's no way to distinguish between the two. That's the loss of information, because when the image is outputted after calibration, after dark subtraction, all the negative numbers become 0. That's how the loss of information occurs. But if we prevent any particular pixel after this subtraction from becoming 0 or less than 0, becoming a negative number, then there will be no loss of information. And that's why you add a pedestal. You prevent, through subtraction, you prevent any pixels from becoming negative. So that output pedestal can help. And let's go look at how that does its job. I'm going to undo this here because we'll compare the new result that we get here in just a moment. Let me go to WBPP. Now I have loaded here the exact same frame I just opened, which is 8668. So this is the same frame that I just operated on here. And this time we're going to put a pedestal. Now the pedestal that we'll put, click on the light frame group. I'm going to put 100. It might make sense to make it a slightly bigger number. It's still a very small number. But this is in, counts. If this was a 16-bit image, then these are, counts that go from 0 to 65,000. So it's a very small fraction of the full dynamic range. Just as another pointer, typically when you're doing broadband imaging, the sky itself might be many hundreds, if not 1,000 or so counts. This is why you rarely see this if you're doing broadband imaging. The sky itself becomes the pedestal value. You never see negative numbers even after dark frame subtraction, and so you don't have this loss of information. But when the sky is so dark through narrowband imaging, and you have these sensors which don't have a very large bias and there's no sky value, you can get negative numbers. So add this pedestal here and prevent all of these problems. That is the idea. I'm going to specify the directory here that we want, which is here, and we will calibrate that frame. Let's be sure I have everything correct. Yep. I'm going to close this, and let's reopen the frame. What the cool thing is that we'll be able to discover exactly what the numbers were on any of those 0 values, which is kind of cool. So let's open up this frame here. Go like this. Let's do this. We will match these two here. Maybe I should zoom in some more. And you know what I'm going to do? I actually am going to show the little zeros here, because now we can discover what the values are. So here we are, now comparing the two images, and let's see, this one right here is a 0, but in this frame here, we can see that the value, well, I'm going to put this in counts instead of in normalized. So to put this in counts, this is a 16-bit image. We're going to put this in the integer range here. Here we go. So what was a 0 in one frame is now 98. That means that it was -2 after the dark subtraction. And by adding the pedestal, we never, of course, get negative. And this one here, 66, which means that, of course, it was -44. But when we look here at the previous version, the dark subtraction with the degradation, there's no way to distinguish. They're both just 0 values, which means it is a true loss of information. And that loss, of course, degrades the final result. So Adrian did actually go through and do what I could do now, but he did it for me here. He has some results where he stacked all of them after properly, of course, putting that pedestal in. There is no degradation of information, and he is well on his way to making a good image. So I hope that you enjoyed learning a little bit about how that pedestal works, and I'm going to bring it back up here. In WBPP, you just increase this. Now, I used 100. You can use 300, 400. As I say, normal sky values are many hundreds or more, so doing a small number of hundreds is a perfectly fine output pedestal value. I encourage you, look at your data, find out if you're having zeros, just pick a frame and just simply subtract it. Find those zeros. If there are any, then you'll know you'll need to use this output pedestal.